Have you ever wondered how we know what stars are made of even though they are light years away? The answer lies in a powerful tool that allows us to unlock the secrets hidden within light itself, spectroscopy. From the vibrant colors of a rainbow to the soft glow of a distant galaxy, light carries a wealth of information. Just as a prism separates sunlight into its constituent colors, spectroscopy reveals light's unique fingerprint. By studying light's interaction with matter, we can identify atoms and molecules.
Spectroscopy, in essence, is the study of how light interacts with matter. It's a powerful tool used in various scientific disciplines, from astronomy to chemistry, to analyze and identify substances. This interaction can take many forms: absorption, emission, scattering, and more.
Think of it like this. Every atom or molecule has a unique set of energy levels, much like a ladder with rungs at specific heights. When light interacts with matter, it can be absorbed, emitted, or scattered, depending on the energy of the light and the energy levels of the substance. By analyzing the pattern of absorbed, emitted, or scattered light, we can identify the substance and learn about its properties. This pattern is like a fingerprint unique to each element and compound.
Spectroscopy doesn't just tell us what something is, it can reveal a wealth of information about it. Temperature, density, magnetic fields, and even the movement of objects can be determined through spectroscopy. This powerful technique allows us to probe the universe, from the vast expanse of space to the intricate machinery of life itself.
Spectroscopy isn't a one-size-fits-all technique.
Infrared, IR, spectroscopy uses infrared light to probe molecular vibrations.
Ultraviolet visible UV-vis spectroscopy excites electrons with UV and visible light.
Mass spectrometry measures the mass-to-charge ratio of ions.
NMR spectroscopy exploits the magnetic properties of atomic nuclei.
Each technique offers unique insights into the world of atoms and molecules.
Imagine light as a wave carrying energy as it travels through space. When this light encounters matter, it doesn't always pass straight through. Instead, it can interact with the atoms and molecules in a variety of ways.
One fundamental interaction is absorption. When light of a specific energy matches the energy difference between two energy levels in an atom or molecule, the light can be absorbed. This absorbed energy excites the atom or molecule to a higher energy state.
Emission is the reverse process. When an excited atom or molecule returns to a lower energy state, it can release the excess energy as light. This emitted light carries a specific energy corresponding to the energy difference between the two levels.
Scattering occurs when light interacts with matter and changes direction. This change in direction can be elastic, where the energy of the light is conserved, or inelastic, where some energy is transferred between the light and matter.
These fundamental interactions form the basis of spectroscopy. By carefully analyzing the absorbed, emitted, or scattered light, we can gain insights into the properties of matter.
Section 5. Inside the spectroscope, unraveling the instrument's mysteries.
The workhorse of spectroscopy is the spectroscope or spectrometer. While the specifics of the instrument vary depending on the type of spectroscopy being performed, the basic components remain similar.
First, a light source is needed to illuminate the sample. This could be a simple lamp for visible light, or a laser for more specialized applications.
The light is then focused and passed through or reflected from the sample being analyzed.
Next, a diffraction grating or prism separates the light based on its wavelength. This creates a spectrum, spreading the light out like a rainbow.
Finally, a detector measures the intensity of light at each wavelength. This generates a spectrum, a graphical representation of light intensity as a function of wavelength.
The resulting spectrum is then analyzed to extract information about the sample. The position, intensity, and shape of spectral features reveal a wealth of information about the composition, structure, and properties of the matter being studied.
Section 6. Reading the rainbow's signature, understanding spectra.
Once a spectrum is obtained, the next step is to decipher its secrets. Just as a detective analyzes fingerprints to identify a suspect, scientists analyze spectra to identify substances and understand their properties.
Spectra are often displayed as graphs, with wavelength or frequency on the x-axis and intensity on the y-axis. These graphs can show distinct features, such as peaks, valleys, and shoulders, each carrying valuable information.
Sharp, well-defined peaks in a spectrum often indicate the presence of specific elements or molecules. The position of these peaks corresponds to the unique energy levels at which these species absorb or emit light.
Broader bands in a spectrum can provide information about the vibrational and rotational modes of molecules. The shape and intensity of these bands can reveal details about the structure and bonding within molecules.
By carefully analyzing the position, intensity, and shape of spectral features, scientists can identify substances, determine their concentrations, and even gain insights into their physical and chemical properties.
Section 7. Spectroscopy in action, from stars to fingerprints. Spectroscopy is a versatile tool with applications in a vast array of scientific disciplines.
Its ability to provide detailed information about matter at a distance and at the molecular level makes it an indispensable tool for scientists across various fields.
In astronomy, spectroscopy allows us to study the composition, temperature, and motion of stars and galaxies light years away. By analyzing the light from these distant objects, we can determine their chemical makeup, estimate their age, and even detect the presence of exoplanets.
In analytical chemistry, spectroscopy is used to identify unknown compounds, monitor reactions, and ensure product quality. From identifying pollutants in environmental samples to analyzing pharmaceuticals for purity, spectroscopy plays a crucial role in ensuring our safety and well-being.
Forensic science relies heavily on spectroscopy for analyzing evidence at crime scenes. By analyzing trace amounts of substances like drugs, fibers, and explosives, forensic scientists can help solve crimes and bring perpetrators to justice.
Biochemistry and medicine also benefit greatly from spectroscopy. From monitoring blood glucose levels to studying protein folding, spectroscopy provides invaluable insights into the complex machinery of life.
Section 8. The limits of light. Challenges in spectroscopy. While spectroscopy is a powerful tool, it is not without its limitations.
One challenge is the inherent complexity of spectra, especially for complex mixtures. Overlapping signals from different components can make it difficult to isolate and identify individual species.
Another challenge is the need for sensitive and precise instrumentation. Detecting weak signals or resolving fine spectral features often requires sophisticated and expensive equipment.
Furthermore, some samples may require extensive preparation before analysis. This can be time-consuming and may introduce contamination or alter the sample's properties.
Despite these challenges, scientists are constantly pushing the boundaries of spectroscopy, developing new techniques and instruments to overcome these limitations and unlock even more secrets hidden within light.
Section 9. Pushing the boundaries, advancements, and innovations. The field of spectroscopy is constantly evolving, driven by technological advancements and innovative applications.
Researchers are constantly developing new techniques and instruments to push the limits of sensitivity, resolution, and versatility.
One area of active research is the development of laser-based spectroscopic techniques. Lasers offer several advantages over traditional light sources, including high intensity, narrow bandwidth, and tunability. These properties enable the development of highly sensitive and selective methods for detecting and analyzing trace amounts of substances.
Another area of innovation is the development of miniaturized and portable spectroscopic devices. These devices are making it possible to perform spectroscopic analysis in the field, outside of the traditional laboratory setting.
Applications include environmental monitoring, point-of-care diagnostics, and food safety testing. These advancements are opening up new frontiers in spectroscopy, enabling scientists to tackle increasingly complex problems and gain a deeper understanding of the world around us.
Section 10. A universe of discovery. The enduring legacy of spectroscopy. Spectroscopy has revolutionized our understanding of the universe and our place within it.
From unraveling the mysteries of distant stars to probing the intricate workings of life itself, this powerful tool has illuminated the hidden world of atoms and molecules.
The journey of spectroscopy is far from over. As technology continues to advance, we can expect even more groundbreaking discoveries and applications in the years to come. New techniques and instruments will undoubtedly emerge, pushing the boundaries of what we can learn from the interaction of light with matter.
The quest to understand the universe and its constituents is a testament to human curiosity and ingenuity. Spectroscopy stands as a beacon of this endeavor, a testament to the power of light to illuminate the hidden wonders of the cosmos and ourselves.